Ma'am, you are not audible.
Hello,
Yes, ma'am, now it is audible.
I'm audible. Okay, so I'm repeating again. Okay, so today we will discuss about the Taylor series and Lorentz series for a complex valued function. So every power series which has a non-zero radius of convergence, it always define an analytic function. And converse of it is also true. It means that if a function is analytic, so we can represent that function as a convergent power series, which will converge to that function in a particular circle. And that particular circle is called circle of convergence. So now we can say that Taylor series is if we have a function fz, which is analytic, a function fz, which is analytic inside a circle, inside a circle, mod z minus z naught is equal to r. So this function may be represented inside this circle as a convergent power series. So fz may be represented as convergent power series, convergent power series fz is equal to an z minus z naught to power n, where this n is going from 0 to infinity. And this coefficient an is given by nth derivative of the function at this point z naught divided by factorial n. And when z naught is 0, if this point is origin, then it is called Maclaurin series. Then this Taylor series is called Maclaurin series. या कह सकते हैं कि अगर कोई हमारे पास कन्वर्जेंस सीरीज है which has a non-zero radius of convergence, so inside that circle mod z minus z naught is equal to r, this power series must be converged to a function, and that function will be analytic. Okay, so next is Lorentz series. Next is Lorentz series. Uh, Here we have take a circle about this point z naught where this function is analytic. But suppose if we have a function which is analytic inside this circle, inside a circle, but is not analytic at a particular point. So we can exclude that point, and in the remaining part of that circle, function is analytic. Then we can also represent that function as a infinite series, but that series will be Lorentz series, not a Taylor series. And in that series, or as you can see here, Taylor series is only containing non-negative power of z minus z naught. But in the Lorentz series, it is also including negative powers of z minus z naught also. Okay, so here, suppose that we have a function fz which is analytic, be a function analytic inside and also on the boundary of the annulus, inside and on annulus z minus z naught r1 r1 r2 for suppose. So this function can also be represented as a infinite series, and that series will be like summation n going from 0 to infinity a n z minus z naught to power n plus summation n going from 1 to infinity bn bn, or we can also write here a minus n upon z minus z naught to power n. And this can also be right in place of these two terms. We can replace these two terms by writing summation from n minus infinity to infinity a n z minus z naught to power n. We can also write it like a n z minus z naught to power n, where this a n is given by, we can write this a n by 1 upon 2 pi I integral along a closed curve C f xi upon z minus z naught to power n plus 1. It should be xi, sorry, it should be xi d xi, where n is 0 plus minus 1 plus minus 2 and so on. And where this c is if it is the annulus about this point z naught of radius r1, and there is another annulus of radius r2. So we are taking here a closed circle C. C is the closed circle lie inside this annulus. So an can be defined as 1 upon 2 pi I integral along this closed curve C f xi. Xi is any point on this circle, on this curve C, and f xi upon xi minus z naught to power n plus 1 d xi, and n is given by 0, 1, 2, and or simply we can say that n is come from the set of integers. Okay, so it is our Lorentz series. It means that if function is analytic at a point, if function is analytic in a closed disk, or if a function is uh, analytic everywhere but it has an isolated singularity at a single point, then we can also represent that function as a infinite series. Okay, so now our next topic is zeros of complex valued function. Zeros of function. For suppose that we have a function fz, and let there is a point z is equal to z naught is called zeros of function fz if fz is analytic at z is equal to z naught, and also its value at this point is 0. If value of the function at z naught is 0, so z naught is called the zeros of function fz. If z is equal to z naught is 0, it may be possible derivative of the function at the same point is also 0. So we can say that derivative of function is 0 until m minus 1 derivative. M minus 1 derivative of this function is also 0 at this point z naught, but its mth derivative at this point is non-zero. All the derivative before this mth derivative are 0 at this point z is equal to z naught, but mth derivative is non-zero. In that case, z is equal to z naught is called the zeros of this function fz, but it is called zeros of order m. In that case, z is equal to z naught is called zeros of this function fz, called 0 of fz of order n. This is 0 of order n. And when m is equal to 1, for suppose m is equal to 1, it means that f z naught is 0, but first derivative of this function at z naught is non-zero. In that case, this z is equal to z naught is called simple zero of the function. So z is equal to z naught is called simple zero of fz. Otherwise, if m is equal to 2, it is called zeros of order 2. If m is equal to 3, it is called zeros of order 3. For suppose we have a function sine z. We have a function sine z. So what will be the zero of this function? If we have a function sine z, you know that it is an entire function. So what will be the zero for this function?
Z equal to 0.
Yes, z is equal to
0. N pi.
yes, n pi, where n is from set of integer. Okay, so this will be 0, and you can see that for n is equal to 0, it is z is equal to 0 is 0 of this function. For n is equal to 1, z is equal to pi is also 0 of this function. N is equal to 2, z is equal to 2 pi is also another 0 of this function. But f dash z is cos z. F dash z is cos z. And you can see that for z is equal to 0, for z is equal to 0, this is 1. F dash at the pi, it is minus 1. F dash at 2 pi, it is 1. So you can see that first derivative of this function is non-zero quantity. They are not equal to 0. It means that all the zeros z is equal to n pi will be simple 0 for this function. So z is equal to n pi is all the zeros of this function sine z, and they all are simple zeros. Okay. We have another function. Suppose this. So what will be the zero for this function? 1 minus exponential z, 1 minus exponential z is equal to 0. So 1 minus exponential z is 0. It means that exponential z is equal to 1. So you can write it 2n pi I. This will be 2n pi I. So z is equal to 2n pi I. N is also come from set of integer. It is 0 of this function fz. Say that it is fz. So this z is equal to 2 and pi I will be the 0 for this function. 1 minus e to power z square. Okay. But you can see here when we are taking its derivative f dash z, f dash z, it will be 2 times 1 minus exponential z minus times exponential z, minus time exponential z. So again, if we are substituting z is equal to 2 and pi I, so when we are substituting here z is equal to 2 and pi I, so f dash 2 and pi I is again 0, but its double derivative, when we are taking its double derivative, this can be write as minus 2 exponential z minus exponential 2z. Double derivative will be exponential z minus 2 exponential 2z. This derivative is non-zero at z is equal to 2 and pi I. It means that m is equal to 2, order of this 0 will be m is equal to 2. So it is not a simple 0, it is 0. Z is equal to 2 and pi is 0 of order 2 for this function. So we can simply say that if Z is equal to Z naught, if Z is equal to Z naught is zeros is 0 of a function fz of order 2 of order m then fz can be write as, we can represent this function fz as z minus z naught, because if z is equal to z naught is 0 of this function, so in that if we are writing this function z minus z naught will be a factor of that function. So we can represent that function like z minus z naught to power m into zz, where this gz is also analytic at this point z naught, and provided that this function is not 0 at z is equal to z naught. So if z is equal to z naught is 0 of this function of order m, so we can also represent this function fz like this. Okay. So it is all about the zeros of the function. Next is singular points. Singular point. A point z is equal to z naught at which function is not defined. A point z is equal to z naught at which function is not defined or function is not analytic at this point. So in that case, this point is called singular point of function fz. Suppose that we have a function fz and this point either function is not defined or function is not analytic at z is equal to z naught, then this point will be singular point. So z naught at which function is not defined, either function is not defined or function is not analytic, then z is equal to z naught is called singular point. Singular point. A rational function of the type, you know that about the rational function. A rational function must be of this type pz upon qz, where pz is polynomial in z, qz is also the polynomial in z, has a singular point at z is equal, you know that this function is analytic everywhere, defined everywhere except the point where denominator is 0. So singular point for this function must be, the singular point for this function, for this fz, must be a point z naught where denominator zz is 0. Denominator zz is 0, but at the same point numerator should not be 0, because agar numerator be 0 ho gaya, so it will be in indeterminate form. So in that case, a point z naught where numerator is not 0 but denominator is 0 will be the singular point for the rational function. For suppose we have function fz, z plus 1, z minus 2, z minus 2, z minus 3, z plus 2. We have this function. So you can see that it is again a rational function, and denominator of this function will become 0 at z is equal to 3 and z is equal to minus 2. So these 2 points, and at these 2 points numerator is non-zero. So these 2 points will be the singular point for this function. So z is equal to minus 2 and z is equal to z is equal to 3 is, they are singular point for function fz. Okay. Now we will talk about how many type of singularities occurs. So basically we can divide the singularity in two parts. Singularity in two parts. One is isolated singularity, isolated, and another is non-isolated. Non-isolated. This isolated singularity is further divided in three parts. One is removable, other is pole, and third is essential. Essential singularity. So first of all, we should know what is the isolated singularity. Isolated singularity. Okay, so point z is equal to z naught. If this point z is equal to z naught is singular point for a function fz, so it will be called the isolated singularity for that function if there exists some delta neighborhood of this z naught where function is analytic at every point except this point z is equal to z naught. It means that if there exists a delta neighborhood around this point z naught and every point inside this delta neighborhood except z naught, function is analytic. यहाँ पे बहुत सारे points है, there are infinite number of points and function is analytic at every point and only this point z is equal to z naught is singular point for the function. Or we can say that in this neighborhood there is no other singularity except z is equal to z naught. Then this singularity is called isolated singularity. In that case, z is equal to z naught is called isolated singularity. This will be isolated singularity for function fz. Okay. So it is the isolated singularity. And if it is not isolated, then it will be a non-isolated singularity. It means that if we will not get any neighborhood, we are not get any neighborhood about this point z naught where this z naught is the single singularity. So we will say that this singularity is non-isolated type. Okay. For example, if we have a function exponential z minus 1. So this function has the singularity at the point where this denominator will become 0. So when we are solving it, we can say that it will be 0 at 2n pi I. This will be 0 at 2n pi I where this n comes from set of integer. So this will be the singularity here. So 2n pi I, अगर इसको हम लिखते हैं 2n pi I कैसा होगा? For n is equal to 0, this will be the singularity. For n is equal to 1, 2 pi I will be somewhere. यहाँ पे ये कोई हमारा 2 pi I. And minus 2 pi I, this will be. Again, we will get 4 pi I. For n is equal to 2, this will be 4 pi I and minus 4 pi I. This will be the singularity. You can see that you can take there a neighborhood. यहाँ पे कोई भी neighborhood आप ले सकते हो. कुछ neighborhood हमें ऐसे मिल जाएंगे around this point where this is the only singularity for this function. So all these are isolated singularities. So each of these points are isolated singularity. Okay. For suppose that we have a function tan 1 by z. Tan 1 by z. You know that tan 1 by z can also be written as sine 1 by z upon cos 1 by z. And you know that where this denominator will be 0, that point will be singularity for this function. So now solving equation cos 1 by z is equal to 0. So general solution for this equation will be 1 by z is equal to 2n plus 1 pi by 2. So we can say that z will be 2 upon pi 2n plus 1. Again, this n will come from the set of integer. So each of these point will be isolated singularity for this function. But you can see that at the point z is equal to 0, at the point z is equal to 0, what will happen at the point z is equal to 0? Function is not defined. At the point z is equal to 0, function is again, it is not defined. So z is equal to 0 is also the singularity for the function. Z is equal to 0 is also the singularity of the function. But if we are taking the limit n tends to infinity of this sequence of singular point, these are the sequence of singular point, एंड सीक्वेंस क्या होगी, n की वैल्यू 0 रखेंगे तो हमारी सीक्वेंस आएगी 2 बाई पाई, n इक्वल टू 1 पे आएगी 2 अपॉन 3 पाई, 2 अपॉन -3, सॉरी, n इक्वल टू -1 माइनस पाई एंड सो ऑन. इस तरह से हमें एक सीक्वेंस मिलेगी, सीक्वेंस ऑफ सिंगुलर पॉइंट फॉर दिस फंक्शन. सो व्हेन वी आर टेकिंग n टेंड्स टू इंफिनिटी pi 2n plus 1, so you can see that in that case this point will be approached to 0, this point will be approached to 0. So you can see that as n is approaching to infinity, yani ki when n is becoming large and large, so this singularity is coming, the singular points are coming close to 0. It means that if we are taking any neighborhood of this 0, कोई भी neighborhood हम अगर इस 0 का contain करें, so that neighborhood of z is equal to 0 is containing so many singularities, many singularities other than this point z is equal to 0. So we will not get a single neighborhood, at least not a single neighborhood around this point z is equal to 0 where z is equal to 0 is only singularity for that function. It means that z is equal to 0 is non-isolated singularity, non-isolated singularity of this function tan 1 by z. ये बाकी जितनी सिंगुलरिटीज हैं, these are isolated singularities, but this z is equal to 0 where the function is not defined, it is the singular point for this function, but it is a non-isolated singularity because we are not getting a single neighborhood around this point z is equal to 0 where it will be a only singularity for that function. Okay. So now we have to define three different types of isolated singularity of the function. And now here we are defining the singularity by using the Laurent series. For suppose that z is equal to z naught is the singularity. Z is equal to z naught is singularity of a function fz, but it is isolated. It is isolated. So suppose that we have this circular region around this point z naught. Function is analytic at every point, but it is not analytic only on this singular point z naught. So for suppose that if we are taking a neighborhood around this z naught and deleting this point, deleting this neighborhood around this z naught, so in the remaining part, in this remaining part, our function will be becomes analytic. And you know that if function is analytic inside an annulus about this z naught, so we can also represent our function as an infinite series in terms of z minus z naught, and that series is called Laurent series. So we can consider here annulus z minus z naught less than r, and there is a r which is greater than 0. This r is anything which is greater than 0. Okay. So the Laurent series will be fz n0 to infinity an z minus z naught to power n plus n1 to infinity. Here I am writing minus n, z minus z naught to power n. So this part of Lorentz series, this part of the Lorentz series is called analytic part. This is called analytic part of Lorentz series, and this part which containing the negative power of z minus z naught, that part is called principal part. Principal part of Lorentz series. It is called the principal part of the Lorentz series. So for this part, if we are expanding this part, means b minus n and 1 to infinity, z minus z naught to power n, this will be b minus 1 z minus z naught plus b minus 2 z minus z naught square plus so on. So you can see here b minus 1 is coefficient of 1 upon z minus z naught, and b minus 2 is the coefficient of 1 upon z minus z naught square in the principal part of this Lorentz series. Okay, so removable singularity, first of all we will define the removable singularity. So removable singularity, by using the Lorentz series, if principal part of Lorentz series is 0, if principal part of Lorentz series of a function of fz is 0, it means that all the coefficient b minus 1, b minus 2, b minus 3 and so on, all will be 0 for all n, for all n. Then z is equal to z naught is called removable singularity, removable singularity of fz, and this can also be defined like, इसको another way में बोले, दूसरी definition अगर दें, so we can say that if fz is not defined at z is equal to z naught, if fz is not defined is this z is equal to z naught, but limit z tends to z naught of this function exists. If this exists, then fz is called removable singularity. Removable singularity. This is called removable singularity. Like for suppose that, इसका एक example अगर हम देखें, so we can say that sin z upon z at z is equal to 0. At z is equal to 0. So this, it is a at z is equal to 0 is removable singularity for this function fz. Is removable singularity for this function, because at z is equal to z naught, it is not defined, but when we are taking the limit sin z upon z, this must be 1. So this is exists, that's why it is a removable singularity. और अगर इसकी Lorentz series भी लिखें हम, if we are writing its series about z is equal to 0, so this will be z minus z cube by factorial 3 plus z to power 5 upon factorial 5 and so on divided by this z. It will be 1 minus z square upon factorial 3 plus z4 upon factorial 5 and so on. You can see here the principal part of this series is 0. कोई भी हमारे पास ऐसा टर्म नहीं मिल रहा है जहां पे z की नेगेटिव पावर्स हो. So by this Lorentz series we can also say that z is equal to 0 is the removable singularity for this function. Okay. Next type of singularity, isolated singularity, is pole. Pole. So if principal part of Lorentz series, if principal part of Lorentz series contain only Lorentz series of Fz has only finite number of terms, then Z is equal to Z naught is called pole of function. This is called pole of the function. It means that if in the principal part there are the term like Z minus Z naught, b minus 2 upon Z minus Z naught square, and it is containing m terms, m upon Z minus Z naught to power n, and rest of the term after this mth term, it means that m plus 1, m plus 2th term, and all that coefficients are 0. So beyond this mth term, all the coefficients of this terms will be 0. In that case, we will say that Z is equal to Z naught is isolated poles for the differential equation. This will be the poles for the differential equation. Okay. And another definition, अगर लिमिट के फॉर्म में इसकी डेफिनेशन लिखें जैसे अभी तक लिखी थी, तो in that case if we are taking the limit z tends to z naught of this function fz, it is always approaching to infinity. And when we are taking the limit z tends to z naught, z minus z naught to power m. Agar if it is z is equal to z naught is pole of order m, so z minus z naught to power m, fz, it is finite. If it exists, if this limit exists, or we can say that it is finite, then we can say that function has a pole of order m. If m is the least positive, smallest, least number for which this limit is exists. मान लीजिए m हमारा है, उस पर ये लिमिट एग्जिस्ट कर रही है, m plus 1 पर भी एग्जिस्ट कर रही है, so we have to take that m which is the least among all the numbers for which this limit is exists. Okay. For suppose that we have a function fz 4 upon z minus 2 to power 5 plus 3 upon z plus 2 to power 4. So you can see here this function has the pole at z is equal to 2 of order 5, and it has also a pole at z is equal to minus 2 of order 4. So you can simply by seeing this, because their principal part से आप देख सकते हो यहाँ पे 5 ये जो मिल रहा है m, so here this 5 indicating that z is equal to 2 is pole of order 5, and z is equal to minus 2 is pole of order 4. Okay. एक और इसमें चीज है कि इफ अगर fz हमारा एक कोई फंक्शन है which has a pole at z is equal to z naught of order n, in that case fz can be represented like phi z upon z minus z naught to power m. This will be this we can write this fz like phi z upon z minus z naught m, where at phi z is analytic at z is equal to z naught, and also phi dash z naught is not equal to 0. phi z naught, it is not dash, phi z naught is not equal to 0 in that case. So then we will say that z is equal to z naught is pole of order m for function fz, for this function fz. Okay. Next isolated singularity is essential singularity. Essential singularity. So essential singularity, if principal part of the Lorentz series of a function fz, if the principal part of Lorentz series of the function fz has infinite number of terms, if that principal part of Lorentz series of the function fz has infinite number of terms, then this point z is equal to z naught, about that we are writing the Lorentz series for this function. So that point is called essential singularity for this function. For example, if we have a function like this 1 upon z, so when we are writing this function z is called its Lorentz series about the point z is equal to 0, it must be 1 upon z factorial 2 upon z square factorial 3 upon z cube and so on. Okay, so z is equal to 0. You can see here principal part will be the part which containing the negative power of z. So you can see here in this series there are infinite number of terms. So here z is equal to 0 is essential singularity. Essential singularity for this function, for function fz at z is equal to 0 of fz. Okay. Suppose that we have given a function fz is equal to z square iota z plus 2 divided by z square plus 1 whole square z plus 3. For this function, we have to classify all the singular points. So classify all the singular point in कहाँ पे इनके singular points हैं and they are which type. Okay. So which type of singularity for that function, for this function. Okay. So for the singular point, because it is again a rational function, so singular point is given by taking denominator equal to 0. So you can say there z is equal to minus 3 and after solving it you will get z is equal to plus minus iota, because इस स्क्वायर में लिखा हुआ है इसका होल स्क्वायर है, दैट मीन्स ट्वाइस ऑर्डर जो यहाँ पे होगा ये कह सकते हैं डबल ऑर्डर. ओके, so z is equal to minus 3 is singular point for this function and z is equal to plus minus is also the singular point for this function. Okay, so and at this point you can see here for z is equal to minus 3, denominator will be numerator will be at z is equal to minus 3, numerator will be minus 3 square minus 3i plus 2. This will be 9 plus 2 11 minus 3i. It is a non-zero value. It means that z is plus 3, z is equal to minus 3 will be the pole for this function, क्योंकि हमने अभी भी पोल के लिए बताया था कि अगर phi z upon z plus z minus z naught to power m के टाइप से हम लिख सकते हैं if it is the pole. And again you can see that यहाँ से इसके लिए भी सेम वे में देख सकते हैं z is equal to I पर क्या बच रहा है हमारा वैल्यू और z is equal to minus I पर if it is non-zero, so it is also the pole. And एक तरीका और है वो भी हम यहाँ पे डिस्कस कर लेते हैं. For suppose that we are writing fz is equal to z1z upon z plus 3. z1z upon z plus 3. Okay. So where z1z is क्या था z square plus I z plus 2 upon z square plus 1 whole square. This is G1z. Okay, and you can see that because at z is equal to minus 3, numerator is non-zero, denominator is non-zero, and it is also analytic at z is equal to minus 3. So we will expand this function as a series about z is equal to minus 3. So about z is equal to minus 3, we are expanding this z1z, g1z, because it is the analytic at z is equal to minus 3. So we can write here the Taylor series of this function g1z about z is equal to minus 3. So Taylor series of this g1z is about z is equal to minus 3 will be क्या होगी z1 value of g1 at minus 3 plus z1 dash minus 3 z minus plus 3 square plus g1 double dash at minus 3 factorial 2 z plus 3, this should be 1, this should be 1 square and plus so on, higher power of z plus 3. Okay, next so z1 minus 3 is a non-zero quantity, you know that. When g1c is divided by z plus 3, it will give us g1 minus 3 divided by z plus 3 plus g1 minus 3 z plus 3 divided by z plus 3 will be 1. Next will be z1 double dash minus 3 upon factorial 2 into z plus 3 and higher power of z plus 3. So you can see that बाकी जो remaining part है ये क्या हो गई z plus 3. This was the function fz. So now we are writing here Lorentz series of this function fz about the point z is equal to minus 3. तो ये Lorentz series है about the point z is equal to minus 3. So you can see that in this Lorentz series of this function fz, all the terms of this series is containing non-zero या कहें नॉन नेगेटिव पावर ऑफ z प्लस 3. यहाँ पे z प्लस 3 की पावर 0, यहाँ पे z प्लस 3 की पावर 1 है, एंड देन हायर पावर लाइक z प्लस 3 स्क्वायर, z प्लस 3 टू पावर 3 एंड सो ऑन. सो ये जो जितने टर्म्स हैं, these terms are containing non-negative powers of z plus 3, but the only negative power in this Lorentz series about z is equal to minus 3 is this, which is z plus 3 to power minus 1. Z plus 3 to power minus 1. So principal part of this function, principal part of Lorentz series for this function fz about z is equal to minus 3 containing only the one term, which is z plus 3 to power 1. It means that z is equal to minus 3 is pole for this function of order 1, and order 1 के pole को भी बोलते हैं simple pole. So z is equal to minus 3 is the pole for the function fz, and which is a simple pole. Okay. In the same way, we can also discuss the similarity for this function at z is equal to plus I, and also with respect to z is equal to I. Okay. ये क्वेश्चन इसको और डिस्कस कर लेते हैं, देन वी विल कम टू अदर मोर क्वेश्चंस. classify the singular point z0 of the function fz is z plus sine z. This is the function. Okay, so first of all, we want to write a series for this function about z is equal to 0. Okay, series of sine z about z is equal to 0 will be z minus z cube upon factorial 3, z5 upon factorial 5, and so on. This can also be written as z 1 plus, this should be 2 minus z square upon factorial 3 plus z to power 4 upon factorial 5, and so on. You can see that this part, when we are substituting z is equal to 0, this part will be non-zero. So we can write it like another function phi z, z into phi z, where this phi z at this point 0 is non-zero because it will be 2. Phi 0 will be 2, which is a non-zero quantity. So in place of z plus sine z, I am substituting here z into phi z, where this phi 0 is non-zero. So fz is exponential z upon z and phi z. And you know that z exponential z at this 0 is also a non-zero quantity. So here we can write it like 1 by z into zz, where zz is equal to exponential z upon phi z, and these two are analytic function at this point z is equal to 0 and z0 is a non-zero quantity. So when we are representing the function like this, phi z upon z minus z naught, and numerator is a non-zero quantity at this point 0. So this upon, you can see that about the pole, you know that if z is equal to z naught, if z is equal to z naught is pole of the function of order m, then we can write that function like psi z upon z minus z naught to power m, where psi at that point z naught is non-zero. So you can see that we are writing here phi z as 1 upon z zz, where this gz is not 0 at point z is equal to 0. And you can see that here in the denominator z minus 0 to power 1, yani m is 1 here. So z is equal to 0 is pole for this function fz of order 1. It means that z is equal to 0 is simple pole for this function. So this is the simple pole. In that way we can say. और आप चाहो तो exponential z की भी लॉरेंट सीरीज लिख सकते हैं. You can also write it like exponential z के लिए क्या हो 1 plus z square upon factorial 2 and so on, and upon z, and zz was 2 minus z square upon factorial 3 plus z power 4 upon factorial 5 and so on to power minus 1. इसको एक्सपेंड करके मल्टीप्लाई कर सकते हैं और वहां से भी आपको पता चल जाएगा प्रिंसिपल पार्ट में कितने टर्म्स हैं. ओके, सो इन दैट वे यू कैन राइट, you can show that z is equal to 0 is simple pole for the given function. Okay. For suppose that, one more question. For suppose that we have to discuss the singularity of the function at infinity. So what we should do? We have a question where we have to show that for the given function, which is z to power 4, 2z plus 1 divided by z square plus 5z plus 2 has pole of order 2 at z is equal to infinity. So as you know that whenever we have to discuss the limit or we have to discuss singularity at z is equal to infinity, we can use the transformation. So here we are using the transformation z is equal to 1 by omega. And we know that the behavior of the function at z is equal to infinity will be the same if we are substituting in place of z 1 by omega, and we will discuss the singularity of that function at the point omega is equal to 0. So now we will discuss the singularity of function at omega is equal to 0. If whatever the behavior of the function will be at omega is equal to 0, it will be same behavior of the function at z is equal to infinity. Okay, now substituting here z is equal to 1 by omega. So our function is f omega, saying that it is g omega. We can say that f of 1 by omega is g omega, and correspondingly change in this function will be 1 upon omega 4, 2 upon omega plus 1 divided by 1 upon omega square, 5 omega plus 2. Okay, so this will be 1, 2 omega cube plus omega 4. 1 plus 5 omega plus 2 omega square upon omega square. So this will be f1 by omega is 1 upon omega square, 1 plus 2 omega cube plus omega 4 divided by 1 plus 5 omega plus omega square. Say that this is 5 omega. So when 1 upon omega, 5 omega. So first of all, we will discuss about this 5 omega. So 5 omega, where this 5 omega is 1 plus 2 omega cube plus omega to power 4, 1 plus 5 omega plus omega square. You can see that at omega is equal to 0, value of this function will be 1, which is non-zero. So we can say that this function f upon 1 omega, f1 omega, या इसी को बोल दें g omega. This g omega can be write like pi omega upon omega square, where pi omega is analytic at point 0 and this value is also non-zero at omega is equal to 0. So by the definition of pole of the function, we can say that omega is equal to 0 at omega is equal to 0 is pole of f1 by omega of order 2. So जैसा behavior function का होगा at omega is equal to 0, the same behavior will be the function fz at z is equal to infinity. So simply it is saying that z is equal to infinity is pole of order 2 for fz. Simply. Okay. So now I am stopping this class here. Tomorrow I will start with the topic residue of the function. Okay. And इस मंडे हमारा जो है